Hi, in this screencast I'm going to walk you through Project 4 and give you some hints along the way. Here's the PDF for the project. You can find a link to this PDF on the assignments page of the course website, and on that page you will also find a link to the zip file for the project. And when you download and extract that zip file in your computer, you're going to see a folder such as this containing these files in it. The folder, as usual, contains the starter files for the problems in the project. It contains a report.txt file that should serve as a template when you write your report for the project, and it contains runtest.py that you should use to test whether or not your solutions meet the input and output specifications. Okay, so now let's walk through the project in some detail. This project is called Guitar Hero, and the goal of the project is to write a program to simulate plucking a guitar string using what is called the Karplus-Strong algorithm. Okay. This is the algorithm that is used to synthesize sounds electronically. Right? Now, when a guitar string is plucked, the string vibrates and it creates a sound. Right? Now, the length of the string is what determines the fundamental frequency of vibration, and we're going to model a guitar string by sampling the displacement of the string at n equally spaced points in time. All right, and these displacements are going to be real numbers between minus half and a half, and then the integer n is going to equal the sampling rate, which is 44,100 hertz, divided by the desired frequency for the sound. Okay, and the number is rounded up to the next integer. So n is basically the sampling rate, which we usually call SPS, samples per second, um, divided by the desired frequency and rounded up to the next integer. Right? Now let's talk about how you model plucking a string and how you model the resulting vibrations. Now, the excitation of a string can contain energy at any frequency, and we're going to simulate the excitation with white noise. And by white noise, we simply mean setting each of the end displacements of the string to a random real number between minus half and half. Okay, so that's how we model the excitation of the string. It's simply white noise, which is nothing but setting each of the end displacements to a random real number between minus half and half. All right. Now, what about the vibrations? Well, after a string is plucked, it vibrates, and the pluck causes a displacement that spreads wave-like over time. Okay. Now, the Karplus-Strong algorithm simulates this vibration, and the way it does that is by maintaining what is called a ring buffer of n samples. All right. So we're going to talk about the structure of this buffer later on, but what the algorithm does is it uses a ring buffer of n samples, and it repeatedly deletes the first sample from the buffer and adds to the end of the buffer the average of the deleted sample and the first sample, okay, scaled by an energy decay factor of 0.996. So here's an example. Here's our ring buffer. So what the algorithm does is, at time t, it deletes the first sample from the buffer, and it adds to the end of the buffer an average of the deleted sample and the next sample in the buffer, scaled by this factor here, 0.996. Okay, so the value that gets added to the end of the buffer is now 0.996 plus a half of zero point 0.2 plus 0.4. Okay, so again, the way the algorithm updates the ring buffer is, at time t, it deletes the first sample from the buffer, and then it sticks to the end of the ring buffer an average of that number that was deleted and the next number in the buffer, okay, scaled by a decay factor of 0.996. All right, so it's 0.996 times a half of 0.2 plus 0.4, is the number that gets added to the end of the list. So at time t plus 1, this is the state of the ring buffer. Okay, so point 2 is gone. Now point 4 is in the front of the buffer, and at the end you have this number here that was calculated using this expression. All right, so that's what we call the Karplus strong update. Okay, and a motivation on why this algorithm works is given here, which I strongly encourage you guys to read. So now what we're going to do is talk about how we model the ring buffer itself. Okay. So let's say we have a ring buffer RB that is what is shown there. Okay, and now let's say we make a call to enqueue with RB as the first argument and the value being 1. Alright, so what does this do to the buffer? Well, we are adding the item 1 to the ring buffer, so the ring buffer needs to look something like that. So 1 is basically added at the index that is given by last. Okay, and but last is 0. So these are the indices, right? 0, 1, 2, 3, and 4. So now the ring buffer is going to look something like that. 1 and dot 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 dot. And since we have added an item to the ring buffer, that's going the size is going to be 1, and then first is still going to remain at 0, but last now will be updated to 1. Okay, because remember that last is basically 1 plus the index of the most recently added item. All right, so now let's say we enqueue RB of 2. So what happens in that case? Well, the ring buffer is going to look like that. Now last is 1, so 2 gets added at that location, and then the rest of the guys are that. And since we added an item, size is going to be 2, and then first remains unchanged, but last is now 2. Okay. Now let's do an enqueue of RB and 3. Now this is going to have the following change in the buffer. You have 1, 2, and a 3 here, dot and dot. The capacity is the size is now 3, and the capacity is 5, but the size is 3 because there are 3 elements now in the ring buffer. First is still 0, and then last is 3. Now let's say we do a dequeue. Right, we do a dequeue on RB. So what effect does it have? Well, that is supposed to delete and return the item at the front of the buffer. Okay, so what happens is, in this case, the buffer looks like that: 1, 2, 3, dot and dot. And since an item was dequeued, the size now becomes 2, and now first is going to be updated to 1. Okay, so first is now pointing to that guy. So that has the effect of removing this. So you don't really remove it from the list. You just update first and last accordingly. Okay. So in this case, first is incremented to 1, and then last remains unchanged. All right. And now let's say you do an enqueue of RB and 4. So this is going to modify the buffer as follows. So 1, 2, 3, and then 4 is going to end up there because that's the index that is given by last. And then since we just added an item, the size is incremented to 3, and then first remains the same, but last is now 4. Okay, now let's do one more addition. So enqueue RB of 5. So this is going to result in 1, 2, 3, 4, and 5. Okay, and then the size is now 4. First remains the same, but last now is incremented by 1. But when you do that, you see that last is 5, which is the capacity of the buffer. Okay, so in that case what you need to do is reset last to 0. Okay, so that's that. And now let's say you enqueue RB and 6. So this is going to result in something like this. So notice that now last has the value 0, so 6 gets added right there. So you have 6, 2, 3, 4, and 5, and then since you added something, this is now 5, and then first remains the same, and last is now 1. All right. Okay. So now let's say you make a call to enqueue RB and 7. What happens in this case? Well, this is when you realize that the size of the ring buffer is same as its capacity. So this is supposed to result in an error. So this is an error. Okay, so I hope that gave you a good idea as to how the ring buffer is represented and how it's manipulated using the functions from the ring buffer API. Okay, so now let's go back to the PDF. So once you have this program implemented, you can test it by running this command on the terminal, which essentially runs the test client that is defined in ring buffer. And if your implementation is correct, you ought to see this result for an input of 10. Okay, and then if you run it with an input of 100, then you ought to see this result here. Okay, so that's problem 1. So now let's move on to problem 2. In this problem, you're going to create a module that is called guitarstring.py that models a vibrating guitar string. Okay, and the module needs to support the API that is given here. All right. So here the basic idea is that we're going to use a ring buffer to represent a guitar string. All right. So let's go through the API. So there's a function called create that takes a frequency as an argument, and what this is supposed to do is create and return a guitar string of the given frequency using a sampling rate that is given by the constant SPS, and this constant is defined in guitarstring.py. All right. So this basically creates and returns a ring buffer with capacity that is calculated from the given frequency, okay, using what I described earlier. Okay, and then there is this function create from samples of init. So here you need to create and return a guitar string or a ring buffer whose size and initial values are given by the list init. Okay, so this argument here is a list, so you need to create a ring buffer whose initial values are basically the values from init. Okay, and then you have this function called pluck that takes a string as an argument. So here string is nothing but a ring buffer, and what the function is supposed to do is pluck the given guitar string by replacing the buffer with white noise. Again, remember what a white noise is. It's basically random numbers between -half and a half. Okay, so just flood this ring buffer with white noise, and that's that. And then there's a function tick that takes a string as an argument. So here you need to advance the simulation by one time step on the given guitar string, and that simply involves applying the Karplus strong update that we talked about earlier. Okay, this is fairly straightforward. And then finally there is this function called sample that takes a guitar string as an argument and returns the current sample from the given guitar string. All right. Now, so that's basically the API that you need to implement. Now, I just want to make one remark here. So whenever you're trying to manipulate or access the guitar string, which is nothing but a ring buffer, make sure that you use the ring buffer's API in order to manipulate or access the guitar string. Okay, you should never probe the internal representation of the ring buffer outside of the ring buffer. You should basically always work with the API, right? So whenever you want to manipulate the ring buffer, make sure that you use the API, the ring buffer API, right, and not directly access its internal representation. Okay, so that's that. And once you have your module implemented, you can test it by running this command on the terminal, and if your implementation is sound, then you ought to get exactly this result for that particular input. Okay, so that's problem 2. Now let's move on to the last problem. So in this problem, you're going to write a program called guitarhero.py, which is basically a client of the guitar string module, and this program is supposed to play the guitar in real time, okay, using in the keyboard to input the notes that you want to play. All right. So if your implementation of the ring buffer and guitar string are correct, then when you run the program guitarhero.py, which is a starter file that is given to you, what you will see is something like this, a keyboard, okay, but it will only have the first 3 keys drawn, right? So your job is to draw the rest of the keys and also implement code that will produce the right sound when those keys are pressed. Okay, but what is given to you is code that actually draws these 3 keys, and these keys will also sound when you press the corresponding characters on the keyboard. Okay, provided your implementation of guitar string and ring buffer are correct. So, for example, if you hit Q, then it presses that key. If you hit W, it presses that key, and then 2 is that key. All right. Okay. So that's what is given to you, and your job is to flesh out the rest of the code. Okay. So let's go back to the PDF. So your task is basically to complete the implementation of guitarhero.py such that it supports a total of 37 notes on a chromatic scale from 110 Hz all the way up to 880 Hz. Okay, and you need so you're going to use the keys, the 37 keys that are shown here to represent the keyboard. All right, from the lowest to the highest note. So the lowest note is Q, and the highest note is the space bar. All right. Okay, so that's that. Now, so the keys are all just characters from this particular string called keyboard. Now, the ith character of the string keyboard corresponds to a frequency that is given by this expression here. Okay, so when you want to calculate the frequency that corresponds to a certain key, this is the formula that you're going to use. So I is basically the index of the key that you press. So Q is, for example, 0. Then the corresponding frequency is calculated using this expression. Right? So Q has a frequency of 110, and then space. If you use this formula here, you'll realize that it has a frequency of 880 Hertz. All right. Okay, so that's that. So now actually what I'm going to do is just walk you through the starter file for guitarhero.py and just give you some idea on what you need to do there. Okay. So here's the starter file, and there's a lot of code that is already provided to you. So there are these functions that are given that would draw a black key and a white key given the right arguments. So each of these functions takes an XY value, which are the coordinates of the lower left corner of the key, and then a boolean is pressed. Which if true will color the key in red, and but if it is false, then it'll be black in this case. And similarly here, x, y are the coordinates of the lower corner of that particular key. All right, and then is pressed is true or false, depending on whether you want the white key to be shown in red or white. Okay, so if this argument is true, then the white key is going to be rendered in red, otherwise it's going to be rendered in white. Okay, so that's that. And then draw keyboard is where is one of the places where you will write some code. So here, there's code that is given to you that draws just the first three keys of the keyboard, but you need to flesh this out such that it draws all all the 37 keys. Right now, index is a helper function that basically returns the index of the key in keyboard. So keyboard is a string, and this function will simply return the index of this particular character in that string, okay, or -1 if that character is not found. So this is going to be useful later on in this main function. Okay, so main is where you will be writing some code as well. All right, so there are some constants that are defined here. And then there is the scale that is set up for the canvas on which the keyboard is drawn, and then you have the string keyboard, which is currently just a string of 3 characters, but you're going to include the other characters here. And then what you need to do is create a list that contains guitar string objects, all right, for each of those keys in keyboard. And then the guitar string needs to be created with the right frequency using the formula that I showed you from the PDF. All right, so you're going to store a guitar string object for each of the 37 keys inside of a list. All right, so now let's talk about this while loop here, which is where all the work happens. Now there is this constant called pressed, which is initialized to -1, and that variable is going to keep track of the index of the key that is pressed. All right, so when the user presses a key, then this condition is true, and then what we do in that case is we get a hold of the key that was actually pressed. And once you know the key, you can use the index helper that we talked about earlier to get the corresponding index. All right. And once you have the index, you can use it as an index into the list that contains all the guitar string objects, and you basically need to pluck that particular guitar string, okay, meaning you want to pluck the string that corresponds to the key that was pressed. Okay, so that's one thing that you need to do here. And then this is where you need to superpose the sounds of several guitar strings, right? So what you need to do here is basically superpose the sound of the key that was pressed along with some keys to the left of the pressed key and some keys to the right of the pressed key. So there is a window of keys that you need to consider to the left and right of the pressed key, and you need to superpose all those sounds. Now this constant here, superposition range, essentially specifies that window size. So it is set to 2, meaning that you want to so when a key is pressed, you want to superpose the pressed key along with 2 keys to the left and 2 keys to the right. Right? So make sure that you use this constant and not hard code the number 2. So the purpose of this constant is exactly that, to specify the size of the window that you want to consider when you're superposing sounds. Okay. So basically in here you need to go through each of those keys or guitar strings that you want to superpose, and you basically want to sample those guitar strings and add all the samples up, and then simply play that particular superposed sample. All right, so that's what you need to do. And then once you do that, and after doing that, you need to advance each of those guitar strings by invoking the function tick on them. All right. So that's basically what you need to do. So consider a set of keys, including and around the pressed key, and then just sample them all and add those values, okay, and play that resulting superposed value, and then tick each of those strings. All right. Um, so that's it. So that's what you need to do in this program here. And so once it's properly implemented, you ought to be able to launch this program here and see the entire keyboard. Right? And then when you press the right keys on the keyboard, you need to hear the right sounds. All right. Okay, so that's the last problem of the project, and then these are the files that you need to turn in. Okay. Remember to write your report, and as usual you want to use this template here that is given to you to write the report, and make sure that you fill in all these sections. Okay. Right. And then finally, do as always, make sure that your programs meet the input and output specifications by running this that command. Make sure that your programs meet the style requirements by running pep8, and then finally make sure that your report has the right syntax, and that it is not too long, it doesn't contain spelling mistakes, and it doesn't contain lines that exceed 80 characters. Okay, so that's it. So I hope you have fun working on this project, and I hope you learn something from it. All right. Okay. Thanks.